Okay, perfect. So welcome everyone to the March ECSA Files. We have Xinyi Kang here today with us, who is an assistant scientist at the Yanti Institute of Coastal Zone Research at the Chinese Academy of Sciences. She earned her PhD in physical oceanography from the University of Maryland in 2019. Sorry, I should let some more people in. And her research focuses on applying numerical modelling to address coastal and estuarine dynamics, such as nearshore circulation, biophysical coupling processes, and storm surge modelling. So I will hand over to you, Xinyi.
Okay,
you'd like to share your screen.
Okay, can you see the slide?
Yeah, that's perfect.
Okay, thank you. Hello everyone. I'm Xinyi Kang from Yanti Institute of Coastal Zone Research, Chinese Academy of Sciences. First, I would like to express my sincere gratitude to Steve Mitchell for inviting me to this online seminar. And my thanks also go to Jonathan for organizing this event and to Alice for hosting it. And today I'm going to talk about two major research accomplishments that I have made since I started working in YC. It's about riverine substance transport and phytoplankton dynamics in a semi-enclosed inland sea. And this work was conducted in collaboration of two of my graduate students and also one international collaborator. The first question is why we care so much about estuarines. Estuarines, where river meet the sea, are crucial for economy and ecology for the nearby regions. As we know, the major external forcing agents, including winds, heat flux, river flow, and tides, could determine the vertical structures of water column and also physical processes, and also influence biological impacts, including water quality, nutrient distribution, fish recruitment, and larvae transport. In addition to these natural factors, human activities such as land reclamation, dam construction, and industrial wastewater discharge further affect coastal dynamics and ecology. The close connection between the physical and biological processes in estuarines have a significant impact on water quality and other various ecological issues. Understanding particle transport dynamics is important to management strategies and environmental assessment. And due to the anthropogenic river nutrient loading and other pollutants discharged into the coastal seas, coastal water have been facing serious water quality issues over the past few decades. Given the importance of particle transport dynamics and also its potential biogeochemical implications, a thorough investigation of riverine substance transport dynamics and also its driving mechanism is really needed. Our study area is a Bohai Sea. It's located in the northern China. It's a typical semi-enclosed inland sea with very weak water exchange. And the Bohai Sea can be geographically divided into 4 sub-areas: Liaodong Bay in the north, Bohai Bay in the west, Laijiu Bay in the south, and also one central basin. There is only one entrance called Bohai Strait to connect Bohai Bay with the North Yellow Sea. 4 important rivers, Yellow River, Ha River, Luan River, and Liao River, contribute water mass into the Bohai Sea with variable river discharges. And polybrominated diphenyl ether is one of the common pollutants in the Bohai Sea. We call it PDE for short. PDEs, they can persist in the environment for a period of long time with long-distance transport and biocommunication, and they also can be toxic to marine organisms. And most of the PDEs in Bohai Sea are mainly from the rivers. And besides marine pollutions, coastal water also face other serious ecological issues such as hypoxia, eutrophication, and algae blooms. And these two figures shows the nutrient and water quality distributions of China coastal water in 2023. So we can see that the coastal regions with important rivers usually exhibit high nutrient levels and poor water quality. Phytoplankton growth is directly linked to nutrient levels, and over the past decade, marine conservations have helped to regulate riverine nutrient loading, while artificial dams also have a great impact for the river runoffs. And this highlights the urgent need for research on phytoplankton dynamics from both nutrient loading and hydrodynamic perspectives. And in our study area, Bahai Sea, in addition to these 4 major rivers, another 6 sewage rivers along the Bahai Sea coast also bring nutrients into the Bahai Sea. And also artificial dams also have a great impact for the Yellow River river discharge. And therefore, in this study, we try to better understand the particle transport processes, nutrient and phytoplankton dynamics in the Bahai Sea. And we try to address 2 major questions. The first one is to reveal the main drivers about the riverine substance transport dynamics in Bahai Sea. And the second questions focus on to study the phytoplankton dynamics from nutrient and discharge effect. The first chapter focuses on the riverine substance transport dynamics in Bahai Sea, and we try to answer these 3 following questions. What are the pathways of the riverine substances in the Bahai Sea? What is the influencing range of the riverine substance? And also, what are the main drivers for the pathways of the riverine substance in the Bahai Sea? And in this study, we applied both numeric model and the surface drifters. Numeric model is the African Lagrangian particle tracking model. This is quite quite common one for numerical studies. And first, let's take a look at the surface drifter tracks. And we deployed 3 drifters in November 2019 and kept tracking from 3 days to 21 days. And the first drifter was deployed in Laizhou Bay, and this one made a southeast moving direction. And the second one was deployed just between the Bohai Bay and the Central Basin, and this one made a roundabout movement. And the third one was deployed just outside the Bohai Strait, and this one first moved to the north and then traveled to the south and the strong northerly winds. Moreover, we also did some simple mass calculations to get the main drifter speed. It's about 30 centimeter per second. It's quite close to the surface circulation magnitude in the Bahai Sea. Later on, we compared the simulated tracks with the observed tracks. So we could see that the black line is the simulation result. For Lagrangian particle tracking model, it's very hard to do model calibration and validation. Even though some bias, we could see that still can capture the movement for the particle dynamics. Moreover, we also applied several basic statistics parameters such as Corey coefficients, mean absolute error, and root mean squared error to appraise model performance for drifter speed, and also for drifter speed for the UV component. And from the statistics information, we could see that even though there are some biases between the simulated and observed tracks and the speed, but we could see that this model still captured the major characteristics of the particle tracking. So our model is still an effective tool to study the particle transport dynamics in the Bahai Sea. And later on in the study, southern particles were released for each major rivers, Yellow River, Hai River, Luan River, and Liao River, on the surface and keep tracking for 15 days. And we choose April to November in 2019 for the study period. We didn't do any simulations for the winter time because for Liaodong Bay in the north, during winter time is partially ice covered. So our model simulation period starts from March to November, and for the whole March we choose for the model spin-up time. So for the result discussion, we only focus on from April to November. And this is the surface trajectories. And also we can see the darker points, darker circles representing the ending locations for the particles. And we could see that the particle transport dynamics from the 4 major rivers in the Bahai Sea show distinct spatial and temporal variations. And for the particles released from the Yellow River, we can see the orange one. In July, it could travel further to the Central Basin. There is a strong gyre currents under the prevailing southerly winds and high river discharge in July. And for other months, particles from the Yellow River were mainly distributed in the western part of the Laizhou Bay. And for the particles from the Luan River, we can see the pink one. For some months, it could still travel to the Central Basin, and in August, it can travel to parts of the Bohai Bay. And for particles from the Hai River, the yellow one, and Liao River, the blue one. So we could see that actually particles for these major rivers, for these 2 rivers, they're like locally trapped in the local regions. They cannot travel to the further areas as particles from the Yellow River and Luan River. Next, we depict the influenced areas as the areas for all the particles traveled through in the specific tracking time. So in the study to represent the influencing range. So actually this figure is the same one as the figure from the last slide. You can just imagine like we use the MATLAB contour line to depict the particle influencing range. And we also did some math calculations to get the area values. So we could see that actually for particles from the Yellow River, for the monthly values, it usually shows the largest values for the influence areas is about 7.53 times 10 to the power 3 square kilometers. And the next one is particles from the Luan River. And the next one followed with the Liao River. And the particles from the Hai River, they usually shows the smallest influencing areas. So now we understand some basic particle transport characteristics in the Bahai Sea. Next, we did some sensitivity experiments to study the driving mechanism. And the first case is to turn off the winds. So we could see that from these 2 figures, there are some like differences. And for the particles released from the Yellow River without winds, especially for this green line is the July 1. July 1 normally can travel to the Central Basin. However, without the prevailing southerly winds in July, the particles were more confined in the local regions in Bohai Bay, in the Laizhou Bay. They cannot penetrate into the Central Basin. And correspondingly, the particle influence areas decreased. And for the particles from the Luan River, we could see that there is like a spatial change from the particle influenced areas. Normally, they have more influence areas in the Central Basin. However, without winds, they more like travel to parts of the Bohai Bay. And correspondingly, the influence areas also decreased. And for the particles from the Hai River and the Liao Rivers, and from the figure, the particle was still trapped in the local regions. However, if we did the mass calculation, we could say that the particle influenced areas increased. And this is due to the confined efforts of wind direction, bay orientation, and the river location. And from April to August, prevailing southerly winds dominate the Bohai Sea regions. And the southerly winds will push particles from Liao River and Hai River that move into the inner bay regions of each subbay regions. Without winds, when we did the current differences, we could see that a northward circulation pattern occurred without winds. So it means that without winds, particles from the Liao River and Hai River, they move to the outer regions of the bay. So from April to August, without winds, the particle influencing areas for Liao River and Hai River increased. However, for September and to the November, in the Bohai Bay is the northerly winds dominant, and northerly winds will push particles from Liao River and Hai River move to the outer region of the bays. And for the current differences, without winds to the outfalling, it will show a southward pattern. This will push particles move to the inner region bay without winds. So for these months, the particle influencing areas decreased. So, however, for the monthly scale, as a result, some months shows that the particle influencing areas increased from April to August. However, for September to November, the particle influence decreased. But on a monthly scale, it still shows an increasing trend for the particle influencing areas for the Hai River, and Liao River. The next case is to tell of the river discharge. So this one is quite easy to understand. And without river discharge, particles from each river mainly confined into the local regions, and the corresponding influence areas value got decreased. And when we get the surface differences, we could see that especially for the Luang River and the Liao River, in the Yellow River, we could see the obvious current differences for these two cases, indicating particles will move into more confined into local regions. And moreover, we also performed the momentum balance analysis, and July 2019 was selected since the particle influenced areas was relatively large in this month. Okay, from the spatial pattern of each important momentum terms and their corresponding values, we could see that for the particle influence areas from the Yellow River and Luang River, Colorius force, pressure gradient force, and also the surface wind stress terms, they are the dominant terms for the momentum balance. And moreover, we also calculate the Rossby number and Ackermann number. Rossby number was less than 1, and Ackermann number was less than 1. This indicates the significance of the Colorius force. And also for July in 2019, for the Yellow River and also for the Luang River, the particles were quite sensitive to wind, and also they can penetrate to the further areas in the central basin. So this indicated that the wind-induced Ackermann transport enhances the coastal shelf connections that can spread riverine substance away from the coastal areas. In contrast, from the Yellow River, from the Hai River and the Liao Rivers, we could see that the horizontal advection, pressure gradient force, surface wind directions, and bottom friction stress, they are dominant terms for the momentum balances. And the Rossby number was less than 1, and Ackermann number was larger than 1. This indicates that inertial force was not dominant, and viscous force prevailed over the Colorius force. This leads to a reduction for the efficiency of the Ackermann transport. And for the Ha River and the Liao River, in July 2019, the particles are more confined into the local regions. So this indicates that the horizontal direction and the dominance as viscous force that override economic transport. This will reduce the coastal shelf connections in the Bohai and Liaodong bays. And I still want to address the study limitation for this chapter. First one is we only deploy 3 drifters in this study area, which is not enough, of course. And for the future work, we will deploy more drifters, especially for the coastal areas to study the coastal dispersed pattern. And also for the river discharge data, we don't have the daily river discharge data for Hai River, Liao River, and the Luan River. So therefore, to force the model, we apply the monthly mean river discharge data. So this will also bring some study limitations for this research. The third one is the study period is really short. We only choose 2019 for the study period. And in the future, we'll expand the study period to study the interannual and seasonal variations for the particle transport dynamics in the study. And moreover, for this current Lagrangian particle tracking model, we only mainly focus on the hydrodynamics. If we want to trace a real substance, a real matter, we have to consider its specific biological or chemical properties, such as if they will decay or they will do some reactions in the marine environment. If so, how can we make it come true in the model to add more modules on that, or how can we to make the simulations more accurate to trace the real matter? So this will need more time and efforts for this part. And this is the brief conclusions for this chapter, and I will not go over it in detail. And the second chapter focuses on the phytoplankton dynamics, and we try to answer these 2 questions. Have the nutrient levels and phytoplankton dynamics in the Bohai Sea changed from 2010 to 2019 due to the pollution regulations? And how does nutrient loading and discharge affect phytoplankton biomass in the Bohai Sea? And in the study, we also applied a coupled hydrodynamic ecological model called FACOM-SAM. FACOM is used to provide hydrodynamic information, and later on, SM model raised what called loading and perform ecological dynamic calculations. So in the end, we could get about 26 data variables, including nutrients, phytoplankton, zooplankton, and dissolved oxygen. And this is the schematic diagram for SAM, including the important ecological dynamics. So let's take a look at the SAM simulation performance. And from 2017 to 2019, we could see that the dissolved inorganic nitrogen, dissolved inorganic phosphorus, and dissolved oxygen, their variations were well captured by our model. And also our model effectively captured the seasonal and monthly variations for nutrients and also chlorophyll A concentrations. And next, let's take a look at the nutrients in the Bohai Sea. And based on the 10-year simulations from 21 to 2019, we could see that from the spatial pattern, the high values occurred in the coastal regions for nutrients, and low values occurred in the central basin. And also phosphorus is actually an order of magnitude than nitrogen. When we refer to the time series of nutrients for each sub-bay areas in the study, we could see that the Liao Bay in yellow, and also the Bohai Bay in orange. This showed high values from 2010 to 2013, and followed by the lower concentrations. And Liaodong Bay in purple, and also Central Basin in green, we could see that there is no significant interannual variations in nutrient levels. And for the phytoplankton biomass, similarly, high values occurred in the coastal areas and low values were found in the central basins. And for the time series from the yearly mean, we could see that for all three bays, Laizhou Bay, Bohai Bay, and Liaodong Bay, for all three bay subbay regions, the phytoplankton biomass was actually low from 2010 to 2013, but increased after 2014. However, for the Central Basin, the green one, it was low values and there was no significant interannual variations. And why the phytoplankton biomass increased after 2014? When we refer to surface temperature SST, we could see that an increasing trend was occurred in Bohai Sea. And in Bohai Sea, there are three dominant phytoplankton groups: green algae, diatoms, and dinoflagellates, and their growth is quite sensitive to temperatures in the model setting. So we think the increasing SST could be one reason for phytoplankton biomass increasing after 2014. And however, we actually don't have enough sufficient observed phytoplankton data for this study. So this is also one study limitations for this one. So this is just a hypothesis. And for the seasonal variations, we could see that for the nutrients, also like high values occurred in the coastal regions and low values were found in the central basin. And high values was found in the summer, and in the summer, this is due to the increased nutrient flux. And in the fall, this is due to the diminished phytoplankton growth. And moreover, we also did some calculations for DI and DIP ratio, and this is called Redfield ratio in biological oceanography. And actually, we found that the double core structures of DI and DIP ratio was most pronounced in the summer. So actually, when we got this information, we were very surprised because this special pattern is quite similar to the hypoxia in the Bohai Sea. So this is also one future study for this part. And also for the phytoplankton biomass, similarly high values in the coastal regions and low values in the central basin. And we found that the high values were found in the summer. Now we have the basic understanding about phytoplankton dynamics in the Bohai Sea. Next, we did some scientific experiments to study the nutrient loading effects on the phytoplankton biomass in Bohai Sea. And we choose the summer of 2019 as a study period due to the peak phytoplankton biomass in this period. And in this experiment, we artificially scaled the DIN riverine DIN loadings for all 4 major rivers and 6 sewage rivers along the Bohai Sea coast for different percentage from 20, 50, 80, 120, 150, and 180, while keeping the DIP flux unchanged and compare with the case base. So we could see that actually for the phytoplankton biomass differences, we can see strong phytoplankton biomass differences occurred in Liaodong Bay and Bohai Bay, increasing the riverine loading, the DIN loading, will promote the phytoplankton growth and vice versa. And however, for Laizhou Bay, actually there's no significant biomass variations due to under the adjustment of DIN loading. The next experiment, we focus on the DIP loading. And for the DIP loading, we could see that actually for all the 3 sub-regions, they showed strong phytoplankton differences under the DIP loading adjustments, and increasing the DIP loading could promote the phytoplankton biomass growth and vice versa. And when we compare the 2 sets of experiments for DIN loading and DIP loading for each sub-regions, based on the phytoplankton biomass and the slope values, we could see that for Bohai Bay and Laizhou Bay, the phytoplankton biomass was more sensitive to DIP loading adjustment than to the DIN loading adjustment. For the Liaodong-Bei, the phytoplankton biomass was sensitive to both DIN and DIP loading adjustments. Next experiments, we focus on the discharge effects, and we focus on the 4 major rivers: Yellow River, Ha River, Luan River, and Liao Rivers. And we choose August 2019 as a study period due to the peak river discharge and high phytoplankton biomass. Moreover, we also perform another 2 sensitivity experiments. The first one is with river discharge and without nutrient loading. And the second one is without river discharge and without nutrient loading. So from the experiments from the Yellow River, we could see that the DIN, DIP, and the phytoplankton biomass decreased around the Yellow River mouth. However, we found an increase in phytoplankton biomass in the Western Liaodong Bay in the case without river discharge and without river loading. And this is due to the weaker circulation, which was caused by the Langkawi River discharge. And this will lead to the phytoplankton retention around these areas. And similarly for the Liao River, and in August 2019, Liao River also shows a little bit larger river flux. It's about like 400 cubic meter per second. We also could see that the phytoplankton variations near the Liao River mouth also decreased due to the absence of the nutrient loading. And we could see that a decrease of phytoplankton biomass is more occurred in the northwestern part of Liaodong Bay in the case with river discharge and with river without river loading. And however, there was no significant change in phytoplankton biomass in this case without river discharge and without nutrient loading. And similarly, this is also caused by the weaker circulations in the northern Liaodong Bay. This will result in like phytoplankton retention. And for the high river in the Bohai Bay, we also see that phytoplankton biomass decrease in the northern part of the Bohai Bay. This is caused by the insufficient nutrient loading via Ha River. And for the Luan River, we could see that there is no significant variations in the phytoplankton biomass. Okay, this is due to the very weak river flux and also like lower nutrient loading from the Luan River. And also for the second chapter, we also want to address some study limitations. The first one is like we do have limited assessment for the observational data. And the second one is even though diatom is also one dominant groups in Bohai Sea, but we actually haven't focused on the silicon dynamics in this study area. And moreover is like for Bohai Sea, actually atmospheric nitrogen deposition is also one great source for nitrogen in the Bohai Sea. But due to the model setting and some like limited observed data, we haven't like included in our model. And the third one, the last one is the neglect of night transparency effects on the phytoplankton growth, because for the Yellow River, it really shows the largest river flux with a lot of sediments. So actually for this kind of water, it's very turbidity. And we haven't considered the suspended sediments effects for the light transparency on the phytoplankton growth. And also there are the 2 like brief conclusions for the 2 questions. So I will not like go over it in detail. And thank you for listening. I will take any quick questions for this talk.
Thank you very, very much, Xinyi. That was really, really interesting. I can imagine there's been a huge amount of work that has gone into all of the modelling and all the research there. So well done. So if anyone has any questions, you're welcome to put your hand up, or you're welcome to pop them in the chat as well. So I'll open it to the floor. I apologise if I say anyone's name awfully. So Sumit?
Yeah, hi. Hello, Xinyi. Very nice talk. Well, I'm Sumit from Stantec in Leeds, UK, and I'm interested in the chapter one of your presentation. You spoke about the hydrodynamic model, and you showed the correspondence between the observed and simulated data. My question is, what kind of calibration was involved? And if yes, then what was the most sensitive parameter for calibration? And could you please comment on the computational expense of the model?
Okay. Thank you for your question. So the model is FECOM Lagrange particle tracking model. We first calibrate hydrodynamic FECOM. So the FECOM generates the hydrodynamic information with water levels, currents, and this one will force the Lagrangian particle tracking model. So for this one, first we do the calibrations of the hydrodynamic. So for this, our model FECOM is already published in 2022. So in the Bahasi, it's published in Steering Course and Shelf Science. So if you need this paper, I will forward to you. So this one mainly calibrate the hydrodynamic for the Bahasi. And for my study, and actually for the Lagrange particle tracking model, it's very hard to do model calibration and validations. So we update the model because for the particle tracking model, because due to the setting of the random walk, we have the horizontal diffusion coefficient. So previously, for the old version of Lagrangian particle tracking model, we set the constant value for the horizontal diffusion coefficient for the random walking modular. However, in the real marine environment, a constant value is not realistic. So we applied the horizontal diffusion coefficient from FECOM to the Lagrangian particle tracking model. So for this one is from constant values to the spatial variable and temporal variable value for random walking calculation. So this is major update for our model to try to calibrate and validate the particle tracking model performance. And for the computational efficiency for FECOM, hydrodynamic is very not wasted. It takes long time. For 1 year, not for 9 months simulations for the hydrodynamic, if we chose, I cannot remember exactly, maybe 64 CPUs. So for 9 months running time from March to end of November, you're like 10 hours. And for the particle tracking model, it's only use one CPU. So for this one, it's short, it's quick, maybe just like 20 minutes to 30 minutes for 1 month. That's my answer. Did you have any more questions?
No, thank you very much. I'm going to look into the paper. Much appreciated. Thank you.
How can I forward this paper to you?
Yeah, I'll find it. It's published. That's no problem.
Oh,
yeah.
Okay.
Thanks.
Yeah, you're welcome.
Thank you. Tim, you got a question?
Yeah, thank you, Xinyi. That was a very interesting talk. My name is Tim Jenayan. I'm from the Leibniz Center for Tropical Marine Research in Bremen in Germany, and I'm a biogeochemist and working on all these effects in the land-ocean continuum, the river effects on coastal zones. So that was very interesting to hear, and that you also not only looking at the physical transport, but also what it does to nutrients, for example, and phytoplankton. Nevertheless, I think it's not really including the dynamics, and I'm always asking myself, how would it develop when you had this transformation, these biogeochemical transformation processes included? And so that's what I'm wondering about. But I found interesting to see from your studies that obviously in the area, the river influence is fairly limited. And I'm asking myself, is it really like that? Or what would happen if you would continue your study for a longer time? And are these dynamics in these particular bays a bit decoupled from the overall Bohai Sea, or one could get the impression that it is a more or less like that the river influence is very limited. Is it so?
I think normally for hydrodynamic setting in the Bohai Sea, we only choose 4 major rivers: Yellow River, Hai River, Luai River, and the Liao River. And normally, Yellow River shows the largest river flux can reach about like at least more than 1,000, like the peak. But because as I mentioned that there are some like reservoir applications for the Yellow River, so human activities have a strong influence on the river flux. And previously, before the artificial dams, the river flux is very high. However, after the reservoir applications, we have like a lower river flux than before. This is for the Yellow River. And for Hai River, Liao River, and the Liao River, for other 3 rivers, normally their river flux is quite low, less than 100 meter cubic per second. For Liao River, in this month, it's very unordinary because I guess because during this one, it's like there's like not very strong, like it's called typhoon passed. And I also look for a lot of information to check for the river flux. It's very interesting that for this month is very high, reached to about like 400 cubic meter per second. But for the previous years, normally it's also like maybe 40, 50 cubic meter per second. For these 3 rivers, river flux effects is very limited. But I think for Yellow River, they have some higher influences on that. Normally in the summer, it's like this shows the largest river flux values. We also like did make how to say. I also have the plots, but I have to find now is to show the differences between. Sorry, let me find one.
I mean, that's okay. You don't have to go into those details, but it's just interesting. Maybe I can add one more question before Steve comes in. What I'm always interested in, and interesting because we are just trying to hire a modeler who really looks at these interactions and does not only consider rivers boundary conditions, but really looks into rivers and river catchments, because there are also spatial and temporal variations of uses that have different effects. I mean, you just mentioned the damming of the Yellow River, and
Yeah.
that would be. Do you include all these variations that you have in the hinterland on the inputs into your model?
So for the Yellow River flux, we have the daily data. So we just put the daily river discharge flux in the open boundary. So for others, well, we haven't taken it in consideration.
Okay, thank you.
Yeah, thank
Steve,
you.
you're next, I guess.
Yep, go for it, Steve.
Is that all right? I'll just come in then. Thank you so much, Xinyi, for sharing your results and your thoughts about the Bohai system. It's been really interesting to hear about them. I've got a particular question about the drifters, in fact, because you showed a photograph of them. Do you think this is? I mean, I just want you to comment on the effectiveness of the drifter study. Really, for example, are the drifters easy to use, and is the data quality you get from these drifters particularly useful? or any other thoughts about the use of these drifters in this way?
And also, Steve, for my paper, the reviewer also asked the same question.
Right.
For the drifter one. So this drifter is quite easy to use. It applies called Beidou satellite as a Chinese, similar to GPS, and it has a horizontal resolution can be within 50 meters. And for the temporal variations, you can set based on your need, and we set as like 15 minutes. So every 15 minutes we can get the location data for that. And when I encountered this question from the reviewer for this paper revisions, I asked the technicians from the drifter company, and I asked about it, and they replied to me that I think the mainly, the accuracy for the drifter locations data is mainly due to the Beidou satellite. So I think another one, maybe we have to pay attention for the drifter deployment is the buoy. So because the buoy length can affect the simulations. So you have to choose a specific length for your study. If you want to track for the surface, you need a shorter one. And also you have to consider the water depths for your study areas.
No, that's very interesting, because the design of the drifter is actually key, I think, in generating good quality data, and there are many different parts of the drifter technology that have to sort of work together. So that's it's interesting to reflect on that. So thank you. And then another quick one, sorry, is what is PDE? What is that? Is it produced by particular types of factories or processes?
I think it's called this one. It's like polybromide diphene ether. It's one chemical. So some people call it PDE for short. This is what I got from from papers from environmental studies. So this is one common pollutants in the Bohai Sea. So this kind of chemical matter is used for I don't know how to translate exactly, to lower the firing temperatures to protect safe. It is really used in some material applications such as decoration, something like this.
Okay, no, thanks. I can.
This is too close to the environmental studies. They have that specific name for compound. I'm not quite similar to this one, but I know it's like a pollutant, and it's now called POPs. It's called persistent pollutant, organic pollutant. POPs is a new pollution in Bohai Sea.
Okay, thanks.
Tim, have you got another question?
Yeah, so just picking up this PD, so you're just taking it as a proxy for you said it's long lasting in the environment, yeah? Just to give an idea on how the environmental effect is. But there's also what my question relates to, maybe a bit related to the other one, saying that we see this relatively limited influence of the river inputs. But also if you think in terms of longer term and maybe also larger spatial scales, what is any effect, for example, in terms of such an environmental problem with PDE, or you could even say nutrients regarding the Bohai Sea and the exchange with other areas? So would you just say all the problem, like for example, the PDE just stays close to the river mouths, and on a larger scale, it stays just in Bohai Sea, but it will never enter the open sea? How long is the residence time of Bohai Sea, and how much exchange is there between Bohai Sea and the South China Sea or East China Sea?
The water exchange in Bohai Sea is very weak, normally like 2 to 3 years to the whole region. So it's quite weak because only Yellow River normally shows the largest
Mhm.
river flux, and for the other ones it's quite small, and also it's like semi-enclosed and only one entrance for Bohai Strait to connect from the open ocean. So this is one principal question for the Bohai Sea, and a lot of researchers use different modeling methods and also different parameters for return time. Normally they like 2 to 3 years. So it's very big one.
So that means when you have an environmental problem, it stays in the Bohai Sea. It's not washed out, yeah?
I also read some like observed and numeric models. So because for Yellow Sea, it normally carries a lot of sediments. If like strong gusts happen, so they can also reach to Bohai Strait on some levels. So we can still see that for the whole one is quite weak, but we can see Laizhou Bay normally with the Yellow River flux, it really shows the strongest water exchange abilities in the Bohai Sea. So on some levels, it can reach to the Bohai Strait, but for the other ones, I don't think they can reach to normally for the local regions around.
Did you ever think about, or did you do a kind of experiment to reconstruct what happened before the Yellow River was dammed so heavily? So I think the impact must have been totally different in terms of dissolved ingredients, but also in terms of suspended particulate matter, and maybe also affecting the residence time of the whole bay and the exchange with the East China Sea.
I haven't done this study, but also artificial dam influences as a great talk for Yellow River, and a lot of studies focus on that. So, and also some other people also asked me this kind of similar question before for the Yellow River. So this is also one key in research interest for the study area. And I think if I have more time and more, I will focus on this topic.
Thank you.
Thank you for your question.
Excellent. Thank you, everyone. Has anyone got a last minute final question before we sign off? Any burning questions? No? No? Okay. Well, I'd just like to thank Xinyi for her excellent presentation. It was really, really interesting. It was great to hear about your work. We are reconvening next month for our next ECSA Files, which will be on the 3rd of April, and we'll be having Gordon Watson give us a presentation. It's an unknown subject at the minute, so it's a mystery, but we will be circulating the details in due course. So thank you very much for attending, everyone, and I hope you have a nice rest of your day or evening, depending on where you are.
Yeah, thank you, guys.
Thank you. Bye-bye.
Thank you. Bye.
Thank you. Bye-bye.
Bye, everyone. Thanks. Bye-bye.